Hello and welcome to our presentation of Gauss Stylization, interactive artistic mesh modeling based on preferred surface normals at SGP 2021. My name is Max Kohlbrenner and this is a joint work with Ugo Finnendahl, Tobias Djuren and Marc Alexa. In this work we present an approach to stylize 3D geometry based on the distribution of surface normal directions. The mapping from a point on the surface to its surface normal, which is a point on the two-sphere, is called the Gauss map. The Gauss image of a surface describes the subset of the two-sphere that consists of all normal directions of the surface. Certain abstract styles have a comparatively simple Gauss image. For example, the cylindrical shape of the monument on the left translates to a ring on the sphere, meanwhile the figure on the right shows only a few clustered regions on its Gauss image, a consequence of its cubistic look. The basis for our stylization technique is the observation that altering the geometry in order to achieve a certain Gauss image can be used to stylize the object. We propose a method that provides direct control over the Gauss image of a surface in order to achieve a certain style, hence its name, Gauss Stylization. We express this target style in terms of a preference function on the two-sphere. This preference function is the main modeling tool in our approach and enables a variety of different styles. We provide an application in which the user can load a mesh and easily apply predefined stylization functions. The tool gives control over all parameters of the algorithm, such as the strength of the stylization. The user can model preference functions over the Gauss image, observe the stylization in real time and adapt the choices in an interactive process. We are going to start by explaining the main ideas behind our method as an extension of a previously defined stylization energy. At first, we were only concerned with the objective of the method, not the optimization. The idea to stylize a shape by moving its normals closer to those of a cube has been introduced in the paper Cubic Stylization by Liu and Jacobson. The easy-to-use method that achieves pleasing visual results brought attention to the normals as a mean for stylization. But how exactly does this approach work? Cubic stylization is an optimization-based method. Given a shape as a surface mesh, the approach adjusts the vertex positions in order to minimize an energy functional. The proposed energy hereby consists of two terms. The as rigid as possible energy term penalizes non-rigid deviations of local neighborhoods from the original geometry, keeping the optimized mesh visually similar to the original one. In addition to this, the authors add a weighted cubeness term based on the L1 norm of the rotated vertex normals. For unit vectors, such as surface normals, the L1 norm is minimal in direction of the coordinate axis. The regularization term thereby favors certain directions for the local rotations, which results in a cubic appearance. The larger the weight lambda, the stronger the alignment of the vertex normals and the more cube-like the geometry. In this work, we propose the use of a slightly different energy functional. It also takes the form of a regularized as rigid as possible energy, but we exchange the L1 term with an arbitrary preference function, called g, and apply it directly to the face normals. Note the change of sign. Higher values of the g function lead to a decrease in the energy functional and are therefore favored. Two main design choices differentiate this energy from the functional proposed in cubic stylization: the phasewise approach and the generalized preference function. We are going to take a moment to motivate both of those decisions. First of all, why should we base our energy function on the face normals rather than the vertex normals? The vertex normals, shown in blue, are averaged over the incident faces. This results in artifacts at sharp edges when minimizing a vertex normal-based stylization energy. Applying cubic stylization on the mesh of a cube leads to unwanted effects as seen here on the blue cube. Switching to an approach based on face normals can overcome this issue. The orange cube no longer changes during optimization. The phasewise approach enables sharper edges and can therefore be used to generate even stronger stylization. Second, the use of a generalized preference function extends the possibilities given by the L1 regularization to a wider range of possible stylization shapes. Let's take a closer look at this preference function. The g function takes as an input a vector of unit length and outputs a preference value. We visualize g functions by scaling unit vectors by their g value as shown on the right. This intuitive visualization works well in both 2 and 3 dimensions and is also the basis for the function modeling tool. For optimization, it is convenient if the derivatives of g can be computed efficiently. During the optimization, the g function aligns phase normals according to its maxima. Depending on the choice of the g function, this results in a different style. Having built an understanding of the visualization of the g function and the relationship between its maxima and the preferred normal directions, it becomes intuitive to read the stylization induced by a given g function. Let's take a look at 2 examples. The left function is symmetric and it has its maxima in direction of a coordinate system. This translates to the surface normals of a cuboid. The example on the right is a bit trickier, but it shouldn't surprise that we find the normals of a triangular pyramid. In our G framework, we can formulate a function that behaves identically to the L1 norm used in cubic stylization up to an additive constant. We show it here on the left. While the L1 norm is preferred in some contexts, since it induces sparsity, we can achieve visually almost identical results with an L2-based G function, shown on the right. In fact, the authors of cubic stylization also work with L2 norms for stylization in their recent SGP 2021 publication. We propose a different option that does not rely on L1 or L2 norms. Instead, we use a preference function that consists of a weighted sum of Gaussians. This enables an intuitive modeling experience, and the function values, gradient and hashing are cheap to compute. Each term in the sum here describes a target direction for the normals. We can extend this to a similar preference function that also covers semi-discrete sets of target directions. We describe it in the paper. Using the sum of Gaussians, the user can easily construct a g function from a set of preferred normal directions. Given the framework, exchanging the g function and removing, adding or manipulating normal directions is also straightforward and can be implemented responsively. The mentioned semi-discrete term can be used to add rings around the Gauss sphere, which favor normals having a certain angle to its axis. Adding or removing these rings gives further possibilities for stylization. As an example, using only one ring with a single downward pointing normal will lead to a cone-like appearance. Since the g function is evaluated on each surface normal, we can also choose to only stylize a part of the mesh, or model individual stylization functions for different parts of the mesh. We believe this to be an important use case and added the option in the interactive tool. This framework for the g function fits a wide variety of different artistic styles and leaves space for the user to become creative. So far, we've been talking about our choice of energy functional. In order to stylize meshes according to this energy, we need an efficient way to optimize it on a given geometry. Let's investigate the Gauss energy a bit further. As in cubic stylization, the energy consists of 2 terms, the as rigid as possible energy as well as a weighted regularization term. The parameter mu determines the weight of the g function and thereby the amount of applied stylization. The as rigid as possible energy depends on 2 sets of variables, a set of rotations r and the vertex positions v. A common way to optimize it uses an iterative block descent scheme, alternatingly minimizing the energy with respect to one set of variables while keeping the other set fixed. In ARAP, this boils down to a polar decomposition per rotation r that can be computed locally and the solution of a global linear equation system. In the global step, the system matrix stays constant, enabling a faster solution using a factorization. This common method to optimize the as rigid as possible energy is fast to compute, and a similar scheme incorporating the regularization term containing the g function is desirable. Both the ARAP energy and the g term are in general non-convex, but this doesn't pose an immediate problem. However, the surface normals of two adjacent triangles, here denoted n1 and n2, both depend on the vertex position of the shared edge E2. As an effect, the vertex normals, and thereby the g values for different triangles, cannot be optimized independently from each other. In a block descent algorithm in the style of the common ARAP optimization, this leads to a global linear equation system with a system matrix that depends on the current vertex configuration. Thereby, it loses the advantage of the constant system matrix. Instead, we propose an approximation scheme for this energy that retains the qualities of the common as rigid as possible optimization, namely a local global block descent with constant system matrix in the global step. To do so, we introduce two sets of auxiliary variables, n star and e star, and optimize the following energy, eg star, using a block descent scheme in three sets of variables. The g function is now applied to the auxiliary normals nf star that are optimized independently from the current geometry V. The auxiliary edges eij star are coupled to the actual edges eij via a squared norm and constrained to be orthogonal to the auxiliary face normals nf star. We want to point out that the auxiliary edges and normals are not expected to converge to the current set of edges and normals. However, the term coupling the auxiliary edges to the edges of the actual geometry drives the real normals to have a higher g function value as well. As in the common ARAP optimization, we apply a block descent scheme on the now three sets of variables. We start with the local rotations r. Since they are only contained in the as rigid as possible energy, they can be optimized in the usual way using a local polar decomposition. The vertex positions also define the edges eij. Reminding us of the as rigid as possible energy, we can see that the coupling term has the same structure of a squared arrow between the edge and another vector. By differentiating with respect to the vertex positions and setting to 0, we again arrive at a system of linear equations with a system matrix that does not depend on one of the three sets of variables. This means our new global step again has a constant system matrix, although the right-hand side is different from the usual global ARAP step. To finish the block descent updates, we need to take a look at the optimization of the auxiliary variables. None of the terms in the energy contains both variables. The connection between the two stems entirely from the orthogonality constraint. This constraint is biconvex, and we use this fact to apply an iterative ADMM update scheme for the auxiliary variables. For a more detailed description of the derivation of these updates, we refer to our paper. This leads us to the final algorithm that is split in three parts: the ADMM optimization, the local step using the polar decomposition, and the linear equation system that results in the updated set of vertex positions. Each iteration of the ADMM update hereby consists of a Newton step and the solution of a local linear equation system. The g function is only part of the Newton step, which means we need a fast evaluation of its value, gradient, and Hessian. While we don't directly optimize the described energy, but work on an approximation, the results of our method consistently decrease the energy. The amount of ADMM steps taken per iteration has an influence on the result, both numerically and visibly. In our experience, a single ADMM update works well, and the results obtained using multiple steps can be reproduced by tuning the other parameters of the method. We only use a single ADMM update, since this allows to provide the most visual feedback, which helps in the interactive modeling experience. After all, our method doesn't only aim at users with a deeper interest in mathematics and/or optimization. Using the intuitive modeling framework, users with all kinds of backgrounds can enjoy stylizing geometry. We provide an open source implementation of our method and invite the viewers to try for themselves. You can find the code along with the paper on our project website. Thank you very much for your attention, and we wish you a lot of fun.